Saturn dazzles us with its rings, storms, and moons, but some of its greatest mysteries lie deep beneath those swirling clouds. Unlike Earth or Mars, where landers can touch the surface, Saturn has no solid ground, no place to stand. Its outer layers are made of gas, transitioning gradually into dense, exotic fluids under crushing pressure. And far beneath all of that, a mysterious heart we still can't fully see. We call it Saturn's core, but what exactly is it? For decades, scientists believed that gas giants like Saturn must have formed around a solid core, a dense, rocky or icy seed that attracted gas from the early solar nebula. But recent findings, especially those from the Cassini mission, suggest a different story. Saturn may not have a well-defined, compact core. Instead, it might possess a fuzzy core, a massive, diffuse region where rock, ice, and metallic hydrogen slowly mix over thousands of kilometers. This fuzziness challenges how we think about planetary interiors. On Earth, we can detect earthquakes to understand our planet's structure. On Saturn, we rely on something much more subtle: ring seismology. As strange as it sounds, Saturn's rings act like a seismograph. When the planet vibrates, whether from internal oscillations or gravitational shifts, those movements create waves that ripple outward into its ring system. By studying the patterns and frequencies of these ripples, scientists can infer what's happening deep inside the planet. In 2019, using data from Cassini, researchers discovered ring waves caused by Saturn's internal oscillations. These readings hinted at a core much larger than expected, possibly stretching over 60% of the planet's radius. But instead of being dense and compact, it seemed to be diluted, spread out, and mixed with surrounding materials. This blurry boundary core, composed of rock, ice, and metal mingled with hydrogen and helium, defies traditional planetary models. It means Saturn isn't a planet with layers like a cake. It's more like a smoothie, blending materials that were once thought to be separate. But how did this structure form? Some theories suggest that during Saturn's early history, massive impacts or intense heat caused mixing between the core and the surrounding envelope. Others believe this is simply how giant planets form in low-density regions of the solar system. Regardless of the origin, it tells us something profound. Planet formation is far more complex than we imagined. Another fascinating question is, how much does Saturn weigh? It seems simple, but measuring a gas giant's exact mass distribution is incredibly challenging. Gravity mapping by Cassini helped provide new data, revealing how mass is distributed throughout the planet. This helped refine our understanding of the core and its composition. Saturn is about 95 times more massive than Earth, but it's also the least dense planet in the solar system. So light, in fact, that it would float in a giant bathtub, if one were big enough. This low density is part of the puzzle. It tells us that Saturn is mostly made of hydrogen and helium, but exactly how those elements behave under intense pressure and temperature, especially in metallic form, is still being studied in labs and simulations. Even more intriguing is Saturn's slow helium rain. Deep within the planet, helium separates from hydrogen and begins to condense into droplets, which then fall toward the core. This helium rain may release energy as it descends, possibly explaining why Saturn emits more heat than it receives from the Sun. In essence, Saturn is still glowing from within, powered not just by the leftover heat from its formation, but also by active internal processes. And yet, despite these breakthroughs, many questions remain. What exactly is Saturn's core made of? How did its internal structure evolve over time? Could its metallic hydrogen layer support exotic forms of matter or magnetism? What role does internal motion play in driving the planet's mysteriously symmetrical magnetic field? Answering these questions will require more than flybys. One day, we may send a probe deep into Saturn's atmosphere, equipped with pressure-resistant instruments that can descend far beyond what Cassini achieved. A future Saturn entry mission could send back real-time data from the heart of the planet, revealing a world we've only glimpsed from afar. At Infinity Beyond, we believe that understanding what lies inside Saturn is not just about planetary science. It's about knowing the building blocks of solar systems, the processes that shaped not only Saturn, but Jupiter, Uranus, Neptune, and even giant exoplanets orbiting distant stars. Because if Saturn has a fuzzy core, maybe those other worlds do too. Maybe the recipe for planets is more fluid, more dynamic, and more surprising than we ever dared imagine. And maybe, just maybe, the deeper we go into Saturn, the more we'll discover about our own cosmic origins.